my name is Joseph Muller, and I'm here with PhD Christine DeLorenzo. She is director for the Center for Understanding Biology using Imaging Technology and assistant professor of psychiatry and biomedical engineering. So I'd like to start, like, my first three questions are pretty similar to one another. I would like to ask you how you got involved with biomedical engineering, like in general, the field, and what about it that attracted you to it?
So growing up, I was really interested in science, particularly physics and chemistry. And when I got to high school, I really enjoyed my science classes, and I thought maybe I would be a physics major in college. When I got to college, I took the same science classes, and I really enjoyed them, but I was looking for an applied field. So I wanted to take this science knowledge and apply it, build something or design something. So engineering was the perfect application for me. I started taking engineering classes. I really enjoyed them. And I started out actually on the material science, sort of mechanical engineering side, because it really incorporated the physics and the chemistry that I was interested in. And then around my junior or senior year, I took an elective, a biomedical engineering course, and I loved it because now I was taking the science background that I love and applying it to problems in medicine. So helping to cure people or helping people live better with diseases, or people who've lost limbs, to help them, get a prosthesis or something like that. And I just loved the fact that I could take all the information that I had learned and everything that I had learned in my courses and apply it to the science of helping people.
Yeah.
And that's how I got interested in biomedical engineering, and I've stayed there ever since.
Yeah, I mean, I started off in biomedical engineering. That's kind of like the exact thing that's attracting me, is like knowing that you can like put it into like work. And,
Absolutely.
But all right, so that sort of covers the next questions. But like imaging specifically, and then going into like the depression, what has motivated you to move in that direction?
That is a great question, because I sort of took a circuitous path. The first project I really did was my master's project, and that was looking at cancer detection using electrical current. So very different from what I'm doing now. I really liked it because I was able to apply sort of electrical engineering concepts to the problem of making cancer detection easier. And that sort of got me to the path of imaging almost, because that was a one-dimensional or two-dimensional electrical signal. And really, imaging is just adding another dimension to that. So from that master's thesis, I then moved on to do my doctoral work. And I said, hey, well, now I've looked at these spectra, I've seen all of these current shifts and things like that. Now I want to actually create an image and see what happens inside an image. So for my doctoral work, it still wasn't in psychiatry though. I actually worked with neurosurgeons and helped them to develop a technique where they could understand how the brain deforms during neurosurgery. Because during neurosurgery, after you open up the skull, the brain actually shifts a little bit. And all the images that they have are from before surgery, so all the images don't show the shift, so they're looking at these images which show this perfect, pristine brain, and then they look at the operating table and the brain is deformed. Yeah, so we developed biomechanical models and imaging techniques to help them update their preoperative images to reflect what's happening in the operating field. And this is what got me started in learning about the brain, because now I was working on the brain on the biomechanics side, but still I started to read about neuroscience, and I got really interested in these patients. Most of them were epilepsy patients who also had problems with, say, depression, or suffered from some other mental illness during some part of their life. So from there I said, hey, we can go in and we can almost cure this epilepsy just by taking out a part of the brain that's responsible for these electrical surges. But the depression side, there's no cure for that. Yeah. So I got really interested in that, and I wanted to apply my imaging background to psychiatry. And that's when I joined a psychiatry lab and sort of learned the background about mental illness.
So has most of your work been in the research? I mean, have you ever done like clinical work with the actual patients?
We have research subjects who we recruit who are either healthy controls or are suffering from some illness that we're looking at in the study. So I interact with the research subjects, but I don't do anything in the clinics themselves. Yeah. The great thing about these labs, though, is that they're multidisciplinary. So my background's in biomedical engineering, but I work with other clinicians. I work with psychologists, I work with psychiatrists, I work with physicists, I work with chemists. So the whole team kind of works on these together. So we definitely, the clinical focus is the most important focus. Because if you're not solving a clinical problem, then it's not worth it.
So I guess in regards to the article that you gave us on like the SSRI,
yes.
Where do you like see the future net going? And actually, I have like multiple questions. So
Sure.
like, the future. All right. So like you said, at the conclusion of it, like you helped like prove that PETs like were like accurate. I don't know, out of my sense.
Okay.
Like, does one experiment kind of lead to another experiment? Like, do you ever have a moment in your career where you're like satisfied with the results? Or
No.
is it kind of like it's continuous?
There's always more questions. There's always more challenges to pursue. And I think even when you do a study and you find a conclusion, you always have to replicate it. You always have to get then a bigger cohort and test it because, statistically you can find an answer that just happens at a probability but is not actually correct.
Yeah.
So you always want to double check and triple check. So for that paper, the really interesting thing was we were trying to focus on understanding who will respond to antidepressant therapy. This is a big problem in psychiatry because if you think of someone who's depressed, most of them lack motivation. It's very difficult for them to get up and do things. So for them to even get themselves to a clinician, to be able to say, I have a problem, help me. Now they're put on a medication. They have to wait 8 weeks to see if that medication will work. That's terrible. Yeah. So what we wanted to do in that paper is use imaging to predict who's going to respond to the antidepressants down the line. So imagine if they came in, they could get a brain scan, and we could say, you know what, this medication isn't right for you, we're going to put you on this one instead. It would save so much time and so much suffering. So for that one, we were particularly using diffusion MRI, because it allows you to map out white matter tracks. But definitely from that study, there are follow-up questions, because we found that you can predict who will respond to these SSRIs. The question is, why is that true? What is it about these white matter tracks that tell you anything about how the SSRIs are going to work? Does that tell you something more about depression? And again, can we do this? Can we replicate this in a larger cohort? So yeah, many more questions to be answered.
So I guess it's like perfect. I'll run into my next question. It's more of like a philosophical question, but like, all right, so the study you did, like the fractional anisotropies and like the white matter, like the amount of white matter. When you're looking at a brain, you're seeing this data, and then you're trying to predict how it affects the function of the brain. And so does your work affect how you see other human, like that they're like sort of pre-programmed in a way, like?
I wish that we had that sophisticated of a model to be able to say, here's your white matter tracks, you're gonna act like this. We can't even really get to the point where we can say, this is what's causing your depression. So if I were at that stage, I would be a little bit happier with what we could do. But the brain, as you know, is extremely complex, and for good reason. It does a lot of things. But that makes it very, very complicated to understand the diseases that we do. Because even, taking two different people who suffer from depression, who've been diagnosed as depressed, their brains can have two different signatures of that depression. And so we're still trying to sort out what is it that causes depression. Can we predict who's going to be depressed ahead of time? Can we intercede beforehand? So we're nowhere near these questions yet, but it's a great question. I mean, we are in some way defined by, we learn when our brain reorganizes itself and when you can grow new connections. So if we were able to know the strength of those connections, you would know how well you learn, for example. So you can say something like that.
You need way more information.
We need way more information. I would love brain imaging to be at that stage where I take a brain scan and now I know everything about you, but we are not there.
Okay, so moving on into like being a researcher, you're obviously going to face setbacks in the things you do. What about like you being a scholar? How do you react to these setbacks in general?
So no one likes setbacks. They're always disappointing. But you have to learn, scientist to sort of be distant from your data, because you can't root for one thing or another. You have to root for the truth. So if you have an experiment and you expect it to go a certain way and it doesn't, you should still be happy because you know the truth, and not necessarily because, oh, okay, this is not what I expected. So it's difficult because we're humans and we're attached, and you want to prove something and you want to get to the next milestone. But it's all part of the learning experience. And sometimes when the most unexpected things happen is when you learn the most, when you say, oh, okay, maybe it's time to refocus, or maybe it's time to rethink the way I'm thinking about this. So it's all in the way that you think about it. And of course, it's really easy to sit here right now and say that because I'm looking at the set of data, like, what happened? It's always disappointing, but you take it and you learn from it. And when you've done it enough times, and in science, you're going to fail enough times, you get used to it. You definitely get used to it.
All right, so like a similar question about yourself. What would you say is a defining feature that makes you a good scientist?
I think I've always been very rigorous in how I approach things. So one of the big things in science is to reduce your variables, right? When you want to test something specific, you want everything else to be held constant. So you really have to keep in mind, what exactly is it that I'm testing here? Can I say in a clear, concise sentence what my test is, what the assumptions I've made are, and what I expect to see? And I like that whole scientific process. I like the idea of simplifying things as much as you can and being really rigorous about understanding what it is that you're looking at. I think it makes everything clearer. That having been said, it's really hard then to go from that little test that you've done to draw bigger conclusions. Yes. But that's all part of the process. Then you get a little bigger and get a little bigger and a little bigger. So I guess I've always been drawn to that process. I've always really enjoyed it, and that's what draws me to this field. I think it's great when you can have as your job something that you just enjoy doing.
Yeah,
that's absolutely.
In regards to like your the current study you're doing, I saw like the grants you received for a certain project that you've been working on. Could you sort of explain that?
Sure. So the grant that I have now, it's also related to depression. It's looking at one of the glutamate receptors in the brain. So that paper that you read, that was looking at one of the antidepressants called SSRIs, or selective serotonin reuptake inhibitors. That is the most commonly prescribed antidepressant. And part of the reason for that is that we don't have a good handle on the biology, so we can't give people targeted treatments. So most of the time, if someone comes in and they're depressed, they get SSRIs. SSRIs will fail more often than they work. So there really is an impetus in the field to find alternative treatments. About maybe 6 years ago, there's this drug called ketamine that they did a study with. They took people who did not respond to SSRIs. These people were severely depressed. They had tried other treatments. They didn't work. And they gave people an infusion of this drug, ketamine. Now, ketamine, unlike SSRIs, acts on the glutamate receptors. It doesn't act on the serotonin. And the amazing thing was that everybody responded. So everybody got at least a little bit better. And 2/3 of the patients met criteria for full remission of their depression. So they were essentially cured. Yeah. So that was amazing. Those are numbers that we've never seen before. And since then, they've replicated these experiments. The response rate isn't quite so high, but it's still impressive. The truly amazing thing about this, though, was we just talked about how it takes 8 weeks for SSRIs to work. This happens in a matter of minutes. So someone's depressed, you give them ketamine, and all of a sudden they start to feel better minutes later. So this is acting on the glutamate system. The question then became, what is the role of glutamate in depression? How is glutamate working? So my project, the grant that I currently have, is to study one of the glutamate receptors and how that receptor works in depressed patients versus in controls, to understand if that receptor is responsible for some of the symptoms of depression that we see. We're trying to tease apart what is it about the glutamate system that affects depression. Why is it that this drug that acts on the glutamate system acts so rapidly to lift depression? So my project is just a piece of that puzzle, looking at one receptor, because there are a lot of different glutamate receptors, and understanding its role in depression.
All right, and like how is that coming along?
So we talk about challenges.
Yeah.
We actually, what happened with that project was we used positron emission tomography, or PET, to look at that receptor. And what happens is you inject a tracer that has a tag on it, and that tracer will bind to your receptor of interest. And then the PET scanner will see where that tracer is because it has that tag. Yeah. So our goal was to look at this receptor in people who are depressed versus controls and just compare them. That's what we were interested in. But as it turns out, this tracer wound up having really interesting properties. So, for example, the first thing you ever want to do is make sure when you give this tracer that it gives you reliable results. So what we did is we did a scan with subjects where we used that tracer in the morning, then we took them out of the scanner, gave them a break, put them back in the scanner in the afternoon. You want to make sure if you test someone twice, the results look the same. It's the same day of the same person, you should get the same result. We get wildly different results. So our first thought was, wow, this tracer is just not reliable. We can't use it. We can't look at the receptor of this tracer. But then what we realized was, actually think that the tracer is changing because there's different levels of glutamate in the brain in the morning versus the afternoon. And this tracer seems to be sensitive to those levels of glutamate. And now, okay, we got off the topic a little bit because we were trying to understand this receptor in depressed versus controls. But what we wound up learning is we might have a tracer that's sensitive to glutamate levels in the brain, which is really cool. Yeah. And so one of the things that we did on our little sidetrack is that this drug ketamine, we said, well, let's use this tracer to tell us what's happening to glutamate in the brain after we give people ketamine. And so then that's what we did. We did a scan in the morning, baseline, then we gave ketamine, and then we scanned again, and we saw that there was this tracer amount decreased significantly in the afternoon scan, meaning that there was a ton of glutamate. We think this is what it means. There's a lot to be worked out. That there was a ton of glutamate that was released after the ketamine, and this gives us some insight into how ketamine is working. So it's all part of the whole process, which is understanding the role of glutamate in depression. It's a little bit sidetracked from trying to learn if this receptor is different in depressed versus
Okay. I guess overall, what is one of the things, the achievements in your career that you're most proud of, or say a moment that maybe changed the way you looked at the field?
Yeah.
Specific experience.
One of the things that I really love is teaching the undergraduates and the graduate students, because
I actually saw a video where you had one guy, a high schooler.
Yes.
And
Ian
got into the top.
The Intel, she was an Intel finalist. We really love doing this a lot. We really love taking high school students, college students, graduate students, and teaching them, because psychiatry is rapidly changing. And these results on ketamine and things like that, you wouldn't necessarily know. It's cutting edge stuff that we really enjoy imparting to other people. So that's what I really enjoy, when there's a finding in the field and we get to kind of tell people about it.
Yeah.
That's really enjoyable for me. I really like
So
that.
that's like the reward. So
Exactly, and people say, wow, I didn't realize ketamine worked that way, or something like that, and you get excited by it, they're excited by it, it's fun.
Most of this has been answered. You were great.
Oh,
Thank you.
thanks.
I think we're good.
Great, thanks guys.